Hello, let me explain the getting of T flip-flop using JK flip-flop. As we know, when both the J and K are 1, we observe toggle condition at Q. So if T is made 1 here, both J and K are going to be 1. That is ideal condition for toggle to happen. So toggling up happens every time the clock is applied here. So that is what the truth table says here. When clock is applied, T is 0, output is 0. When clock is applied and T is equal to 1, toggle will happen. That means output switches from 0 to 1, 1 to 0 after every clock. So as we can see the logic symbol here, J and K are shorted to be applied as input to T. Then clock is applied here and Q and Q bar are the two output, based on which module declaration is made. Module is the keyword and T flip-flop TFF is the name given to this circuit. Inputs are clock and T, output are Q and Q bar. So we are going to represent this program in behavioral modeling. So the outputs Q and Q bar are called as registers. So register is a data type which will declare the outputs so that the outputs will be held at a value till the change takes place. Now we have got two more variables introduced as register, clock div and another variable as div. Div is a array of 24 to 0 bit. Clock div is a single bit. These two variables have come up because internal clock that is available in FPGA kit will be normally faster. So we have to reduce the clock to the desired value. In order to divide the clock, we have got one always block here. Always is the keyword used for representing a block of statements which are sequential in nature in behavioral modeling. At is the operator which will allow always to execute every time the input changes. So this is posedge. Posedge means positive edge application of the clock. So whenever positive edge application of the clock happens, these two statements are executed. That is, div keep on incrementing up till the 24 value. That means this clock leading edge starts and the trailing edge will be after 24 clock pulses. That means the clock frequency is divided by 24 by this always block. Now we will go to another always block. Here actually T flip-flop operation would take place. Now we are applying the clock div instead of clock because clock is divided as a smaller value. So smaller clock positive edge we are applying to the always block where T function is described. So if T is equal to 0, double equal you have to observe here. That means is it equal is the relative operator. If T is equal to 0, begin will start, output is made 0 and its complement is 1 and we end there. Otherwise, that means if T is equal to 1, Q will become Q bar. That means Q reverses, complements and Q bar complements again of Q. Here Q became 1 in the sense here it becomes 0. If Q value becomes 0 means here Q bar value will be 1. So, like that when T is equal to 1, that is this condition, else condition, Q keep on complementing, Q bar keep on complementing. That is where we end the else here. If is ended here and the end module is the end of the entire description. So this is about D flip-flop. Now let us go to another flip-flop which is T flip-flop. This is more interesting. As you can see, SR latch is converted into D flip-flop. As you can see, S and R are shorted by the input of D. D is applied to S. To R, same D is applied through an inverter. That means when D is equal to 1, S is equal to 1 and R is equal to 0, Q will be 1. When D is equal to 0, S will be 0, R will be 1, Q will be 0. That means Q follows D. That is, when D is equal to 0, Q is equal to 0. When D is equal to 1, Q is equal to 1. Hence, this latch, I call it as latch because I have got enable here rather than a clock. So, this is a latch because I have used enable here. Now, let me check the truth table. Enable is 1. If D is equal to 0, output is 0. If enable is 1, D is equal to 1, Q is going to be 1. That means output follows D. Now, we will see the module here, program. Module is the keyword. DFF is the name given to this circuit. Inputs are D and enable. Output Q and Q bar. Close the bracket and semicolon. So, this part is actually module declaration. So, here I have got three intermediate signals. What are intermediate signals? Intermediate signals are those signals which are not declared under module. So we have to separately declare them as wire. Wire, we know it is a data type which will declare some of the signals as intermediate signals. Now, we have got assign statements because we are now writing this description using data flow modeling. How many gates are there? So many assign operation will come. First of all, let us take this gate, that is not gate. We are assigning S2 is equal to not of D. Tilde means not of D. Then S1 is NAND operation between D and enable. D and enable are NANDed to get S1. R1 is equal to, assign R1 is equal to NAND operation between enable and S2. S2 and enable are the NAND operation to get R1. Now, we are going to assign Q. Q is the NAND operation between Q bar and S1. S1 and Q bar are NANDed to get Q. Then Q bar is obtained by NAND operation between R1 and feedback of Q. R1 and Q are NANDed to get Q bar. So end module. Here there are no always statements. So only one end is there, that to end the module. So this is how Verilog code is written to describe D flip-flop or data flip-flop, or you can call it as delay flip-flop also. Using an SR latch, we are shortening S and R from D using an inverter. So like that, D latch can be developed using an SR flip-flop. Thank you.